Okay, thank you. First, thanks for the invitation to speak here. It's my first time in Florence, and I'm really enjoying it. So I'm going to be telling you about this paper that we put out earlier this year with my collaborators, Alberto Guijosa and Jait Olivas. And it's in the context of holography and entanglement entropy and related things. So this is the outline of my talk. I'm gonna start telling you about what is our motivation. And essentially, our starting point is what is known as subregion duality. Is this equivalence between the reduced density matrix for a subregion in the boundary with a certain subregion in the bulk, and why there are some puzzles in the standard picture. Then I will show you how we resolve these puzzles, arriving to a more refined version of this duality. Then I'm going to tell you about the field theory interpretation, some generalizations, and then some open questions that we are still thinking about. Okay, so please stop me if there is any question along the way. So let me start with the basics, although I have this slide, but for this audience, I don't think this is really necessary, but let me just say a few things and move on to the main part of my talk. So as I told you, we are interested in topics related to entanglement entropy and how gravity emerges from entanglement. So there is a lot of progress in the last 10 years or so about this connection between entanglement and connectivity of spacetime. This is more concretely realized in ADS-CFT, where, as you know, entanglement can be computed very easily using the areas of some codimension 2 surfaces in the bulk. And well, in the field theory, this is the quantity that I'm interested in. So I define a subsystem, then I define the reduced density matrix by tracing over the degrees of freedom of the complement, and I can compute this bond Neumann entropy. In the bulk, as I said, the RT prescription tells us that this is computed by the area of some minimal surface. And so this formula is really nice. It generalizes what we know as the Bekenstein-Hawking entropy for black holes. And already from this formula, you can already see that how entanglement might be connected with geometry. In particular, if you know all the pattern of entanglement of a state in a holographic CFT, then it's very natural, and there is a precise way in which you can reconstruct part of the bulk metric. This was realized a couple of years ago. And then more remarkably, not only geometry, but also the dynamics of geometry, that is Einstein's equations, turn out to be encoded by the rules of quantum entanglement in the dual theory. Another aspect that I want to highlight is that we have used some properties that are only true for holographic states. These are the so-called entropy inequalities that, for example, the monogamy of mutual information or higher order party inequalities, to constrain or to use them as a criterion to learn or tell what possible CFT states have possibly a gravitational description. Okay, so let me just now move to subregion duality. So as I was telling you, this is a proposed duality between the reduced density matrix of a subsystem in the CFT with the subregion in the bulk that is called as the entanglement wedge. So here in the previous picture, I only draw a time slice, but you can extend this to include time. And here, so what is, well, it is known that the reduced density matrix is actually a characterization of not only A, but subsystem A, but also of all the domain of dependence. And similarly, in the bulk, there is a region that you can draw that is the domain of dependence of a slice that is in between the RT surface and the subregion that you have in the dual. So this is a proposed duality that implies a one-to-one map between one side to another. Probably what it is more known for is from going from the boundary to the bulk. That is known as bulk reconstruction. That is use CFT data associated to some subregion. You can use some correlators spread out, or why not? And then you try to reconstruct locally what your bulk fields are doing inside the entanglement wedge. So as you probably know, the first attempts to make this concrete were limited in the sense that they used only causality, bulk boundary to bulk propagators. They were successful in a limited sense, that in the sense that they were able only to reconstruct part of the entanglement wedge that is called the causal wedge. That is a smaller region. And more recently, well, it was understood that holography really acts as a quantum error correcting code, and using these tools, it was that only then that it was this paper and others, they were able to reconstruct, find a complete map between CFT data and local bulk operators within the entanglement wedge. Okay, so let me tell you why, at least from my perspective, this is important. So I'm just going to give you two reasons. One is because subregion duality provides a toy model for studying aspects of black hole physics. So there is a precise sense, for example, in which you can map the interior of the entanglement wedge to the exterior of a hyperbolic or topological black hole. This is the so-called Cassini-Huerta-Myers map. And then using this map, you can ask the same type of questions that you normally ask for black holes, like information loss, unitarity, and so on. So that's one sense in which why I think this is important. The second is because studying properties of this subregion duality can, in principle, help us to put constraints on effective field theories that arises in the bulk. So just to give you a hint on how can we use that. Well, subregion duality, two properties that subregion duality obey is the nesting. That is just the property that if two subregions are nested in the boundary, then the entanglement wedges must be nested as well in the bulk. And the other property is the causal wedge inclusion. That is the property that generally the entanglement wedge is larger than the causal wedge. So these properties are quite, you can prove them quite easily in Einstein gravity, for example, but if you have stringy corrections where you integrate out some heavy modes, for example, you arise to some corrections over Einstein gravity. And then generally in these effective field theories, what happens is that the graviton, at least one mode of the graviton can propagate faster than light. So things about causality are not so simple. So you can try to use these properties, and they will put constraints on these higher gravity couplings that you get. Okay, so let me now go to explain two puzzles. One puzzle was pointed out a couple of years ago by Ning Bao and collaborators. The puzzle is that apparently there are some, in particular, they pointed out that some strings that are dual to Wilson loops, there are some strings that even though they are anchored inside in the region of interest, they can exit, they can probe parts of the geometry outside of the entanglement wedge. So here, this is a picture that is taken from that paper. Here, they are thinking about a 5-dimensional bulk So the region here is let's take this strip, an infinite strip that is infinite in 2 dimensions, and it has a finite extent in the other. And then, so here I'm suppressing one of the directions. And then there is a Wilson loop, a space-like Wilson loop that is circular, that extends in the 2 of the infinite directions. And that is an example of a string that can probe deeper into the bulk than the RT surface. So they reached this conclusion that I'm writing down here. They concluded that either the reduced CFT state encodes information about the bulk beyond the entanglement wedge, or the other possibility was that the reduced state actually fails to contain information about this two-dimensional surface anchored in that region. So the second possibility is rather surprising, and because after so many years, we have had many precision tests of that the recipe for Wilson loops is true. So they went on to suggest that maybe the first is true, and maybe we can use these Wilson loops to learn to probe this part beyond the entanglement wedge. This is surprising because if you take this analogy with black holes seriously, that means that there are some certain observables that, at least classically, can probe the interior of a black hole, which is rather surprising. So this is the first puzzle. The second puzzle is that, the one that we pointed out in our paper, is that if you go now from, I was telling you about going from the CFT into the bulk. Now, if you go the other way around, if you go from the bulk to the boundary, then there is also a puzzle that we arise. So the puzzle is that if you try to compute a correlator, say a 2-point function or an n-point function, in principle, the reduced density matrix should be enough to compute such correlators, provided that the insertion points are within the region, right? However, if you go to your favorite prescription to compute correlation functions in holography, so for example, the JKPW, then it turns out that you require information not only from the fields inside the entanglement wedge, but also from the exterior. So here I'm summarizing the way we compute correlators. So you equate the partition functions, and at least at large n, you can approximate this in the gravity side using the saddle point. And it boils down to compute this on-shell action. And then you can differentiate and so on and compute the correlators. But already at this level, you can see that in order to compute this quantity, you need information beyond the entanglement wedge. First, you need to solve for a classical solution for bulk fields. This classical solution requires boundary conditions, not only in the subregion, but everywhere. And then you need to evaluate this integral that contains information about fields outside. So apparently this recipe needs information from beyond. The same issue arises if you try to use the extrapolate dictionary. So if you want to compute first a 2-point function, for example, in the bulk, and then try to take one of the points to the boundary. The issue is that in order to use that prescription, you need the bulk Green's function. And also, in order to specify the bulk Green's function, it's important to know the boundary conditions everywhere.
Sorry, can I ask?
Yes.
So this is a real-time correlator. It's Lorentzian
Yes.
correlator. So it's not just the standard JKPW. You have to put some information about the initial state. And
yeah, I'm talking about real time. Yes.
Yeah. So then, if you keep the initial state fixed and you just change the sources in the complement, the correlator should not change, right? In the region you're considering. So isn't that the case?
If you add sources in the complement,
but you do it while being careful to keep the initial state the same.
Well, if you add sources, it will back react at some point in the future.
Yeah, exactly. But that will not affect
time.
your region, the region you're considering, because it's space-like with respect to the complement.
Well, for that case, I think it's true. But in principle, you should be able to compute correlators not only in the region, but also in all the domain of dependence. So at some point, I think you will
okay.
some
Maybe I will ask you again later.
Okay.
Thanks.
Okay, so since the issue here is about integrating out some of the degrees of freedom, then we thought that, okay, let's start from the equivalence between partition functions and let's see what can we learn from that. And we reached a possible solution using a variant of what is known as Wilsonian integration. So before I explain what we did in practice, let me just mention what we normally understand by this Wilsonian integration. So in a field theory, you can probably you are interested sometimes in having a low energy description of any field theory. Normally, that's one of the interests. And what you do is to start with the full path integral. And then you can define an effective action that is valid below certain cutoff. And the way you do it is to integrate over modes with momentum modes above this cutoff. So in that way, you can define this effective action, and then well, that's one way to do it, right? This is in general quantum field theories. In holography, there is also a way to implement this. The idea is that in holography, the radial direction codifies this RG direction. And the idea is to integrate out modes up to certain radial cutoff. So that was done like more than 10 years ago. You start with your gravitational partition function. First, well, you can generally need to add some UV counter terms to regularize, to remove volume divergences near the boundary. But the idea is to now integrate or divide your path integral in two regions. Let's define some Z lambda, some radial cutoff. And you divide your path integral in these three. So modes below the cutoff, modes above, and the fields on the interface. And then the idea is to do the integral of the UV modes and define an effective action that is valid below that cutoff. So at the end of the day, you end up with this path integral. So in a figure to illustrate this, here I'm drawing what I'm really doing. So if you imagine this is the radial direction, like in Poincare coordinates, where z equals 0 is the UV and z to infinity is the infrared. You can also have a black hole, in which case you have a horizon here. But the idea is that you perform this path integration up to some cutoff, and then you arrive to an effective action. The effective action is you have a bulk piece, but you have also a boundary term here that encodes this RG flow. Now, the idea is that we want to use this now applied to the entanglement wedge in a certain way. So first, let me just point out that renormalization of entanglement entropy is already understood. So Marike has some papers on that. At least the part of where you introduce this boundary counterterms. But here, my focus will be a little bit different than that, because now, instead of trying to integrate over UV degrees of freedom, I'm going to try to integrate over some IR degrees of freedom. So the simple way to generalize this is to, okay, let's split the partition function in the same way. But let me now integrate over this, over IR. You can do it, and then you get a path integral over this this portion of the manifold, supplemented by some infrared action at this interface. This is just a simple example, but really what we are interested in is in the entanglement wedge. So what we did is to actually integrate not up to a surface of a constant set, but actually to the space-time region outside of the up to the lids of the entanglement wedge. So that is the prescription, and then as a result, you can mimic what you did here, and you get a partition function with a bulk piece, UV piece that includes all these boundary contour terms to make this finite, and now an infrared piece that that is defined over the lids of the entanglement wedge. Okay, so to have a picture here I'm suppressing the time direction, but to have some sense of what we're doing is we are integrating over this portion here. And then, as I said, we get, as a result of this integration, we arrive to a boundary action defined on the surface. So there are one big conceptual insight here is that in this more refined version of what we call subregion duality, now entails this identification that now the reduced density matrix will be dual to, okay, the region are all the bulk fields that live inside the entanglement wedge, but is now supplemented by this infrared action. So we can understand it as follows. So in the field theory, when you compute a reduced density matrix, it is important to specify what is the subset of degrees of freedom that that you want to trace out. But it is also important to specify what is the global state. And precisely this infrared action is not only until we know what this infrared action is that we actually know what is the what was the global state that we started with. So this is actually nice because this solves the two conceptual puzzles that I pointed out. First, this boundary term, it provides boundary conditions for fields that live within the entanglement wedge. So if I do a variational principle, I can solve my classical equations of motion, and this boundary term will encode some boundary conditions. And then I can use my recipe to compute correlators, and everything is fine, provided that my sources that I'm interested to turn on are within this region. And second is that in principle, this infrared action has some information about the global state. That information is integrated, so it's not the full information, but is some. And this information has potentially the information about these objects that I told you that can exit the entanglement wedge. And okay, that is not nice. I will show in some examples how this happens. But let me tell you about the physical interpretation. So we have an infrared action, and the way we interpret that is that now we have the region inside the entanglement wedge, but now it's coupled to an end of the word brain. Okay, so this is very similar and reminiscent of the usual story of brain words in Randall syndrome. Yeah. In that case, however, you integrate, you have a brain and you get a word volume theory that results from integration over the UV. Here is similar, but here we get an action that comes out from integration over IR degrees of freedom. And the second point that I wanted to mention here is that this is actually, in practice, the entanglement wedge version of what we know as the membrane paradigm for black holes. So we are really exchanging the degrees of freedom in this case, exterior to the entanglement wedge with a membrane that lives on this RT surface or the horizon in the case of black holes. Okay. Right. So let me now give you a hint of how to interpret this from the field theory. So we can, I mean, all of this was done in the framework of partition functions, and you can try to ask, okay, what if I do the same exactly in a field theory? So you can do it. There is several ways to integrate spatial modes. Here I'm showing two examples here, and like as Kyriakos said, here I'm interested in doing some real time. So I'm using here the Schwinger-Keldysh contour, where you essentially you prepare a state. You need to define the initial state and the final state, and the way you do it is by Euclidean partition function. So you add these Euclidean parts to the contour. So this is time here. This is imaginary time, and this is just space. So one way in which we can reduce is to integrate to a space-time strip, where I'm integrating over in one spatial direction up to a strip, as drawn here, and then you can carry out this integration. At the end of the day, you get a path integral supplemented by these boundary actions at the two edges. The case more analogous to what I was telling you about, that is when you reduce to a causal diamond. Again, you start with the full path integral, and you carry out the integration over the exterior of this diamond. You end up with this path integral of some theory inside and some boundary term. In these two cases, the novelty here is that the theories that live here are defined over a manifold with a boundary. So I'm calling them BCFT. More generally, they are boundary QFTs. In order to have a really BCFT, you need the specific boundary conditions, but I'm just calling them this for generality. And one thing to point out is that not only I have those theories with the boundary now, but also I have these two integrals remaining over fields at the edges of my manifold. So that implies that within these integrals, the boundary conditions of this boundary theory are changing. So here, these two cases can be interpreted as an ensemble of BCFTs with different boundary conditions, Dirichlet boundary conditions. Now, what does all of this have to do with the bulk? Well, if we assume that these boundary QFTs or boundary CFTs have a holographic dual, then we know examples of this mapping that holography works in these cases. This had been proposed by Tadashi and some people. What happens there is that in the bulk, you get a description in terms of a bulk that is supplemented exactly by an end of the world brane. So in these two examples that I showed you, you get a bulk, a piece of the bulk, now supplemented by these branes that I'm drawing here in green. Now, this holographic dictionary is still under construction. This is just a heuristic argument that I'm giving you here. And what I'm wanted to point out is that even though this bears some resemblance with what I told you about from the bulk perspective, there are some differences. So first, notice that with this extra path integral that we have as I said, an ensemble of BCFTs, and that means that using what we know about this dictionary, that going from the boundary to the bulk, that the location of these end of the world branes are not really fixed, but they are varying. While what we did from the bulk perspective, we integrated out up to the surface that we defined. So in that context, the location is fixed. It's fixed because we said, okay, let's integrate up to this point. That's one difference. And the other difference is that the bulk geometry. The bulk geometry really, from the bulk perspective, is just a portion of the global bulk geometry that I started with. But in this case, it's not really. So depending on boundary conditions and depending on many things, you can have bulks that not even resemble ADS. So in order to have ADS, you need to have very specific boundary conditions to preserve some of the conformal symmetry and so on. But that is not the case from these path integrals that I arrive here. So in order to make this connection between boundary and bulk, then we went on to analyze what sort of boundary conditions are we entitled to impose in our prescription. So here we start with the path integral. You can think of this as in the bulk or in the boundary. And you can carry out the IR integral to obtain the boundary term. Here I'm showing you the structure that we get in general. In general, we get something that looks bilocal. So it's not a very simple action, but it's non-local in general. But nevertheless, what I wanted to show you here is that when you use the variational principle in the sum of this bulk term with the IRPs that you get this boundary term here, a boundary term that looks like here. So in order to make this vanish, we have two choices. One is to impose that this variation is 0 at the interface. This is the standard Dirichlet boundary condition that I was telling you about. But we have another choice, that is that this big parenthesis here vanishes. This looks like Neumann, but where I fixed the derivative in some way, but it's really a very non-local generalization of Neumann, because this term here is non-local. So when can we use one or the other? That's the point. What's going on? Oops. Yeah. So I have a figure here to illustrate that. The idea is that we are splitting the path integration in two regions, and we have an extra path integral over these values at the interface, right? So normally you can solve for the value of the classical field in the two regions, right? So that's what this represents here. And then at the end of the day, you integrate over all possible boundary conditions, Dirichlet boundary conditions at the interface. Once you do that integral, that average, is that you get this smooth solution that is the global solution. Okay, so if we don't do this integral and we first do the solve for the classical fields, then we can impose Dirichlet boundary conditions. Alternatively, we can choose to start carrying out this path integration over this value at the interface. Then in that case, the second boundary condition arises as an average. And in that case, once we definitely do this path integral over this value at the interface, then we end up with one single theory. one single theory with a new boundary term, such that it encodes this Neumann boundary condition. So the key point here is that I can do this both bulk in boundary, and in that case, in both cases, I no longer have this extra integral. I have only one BCFT with one specific boundary condition, and in the bulk, I have also one brane with no extra integration over the boundary modes. And the difference that I was telling you about, they disappear, and then we expect that the two descriptions match coming from the boundary or the bulk prescription. Okay, so we did a couple of concrete examples in the paper. Here I'm showing you a simple case that you can do is take a scalar field with no dynamical gravity, just a scalar field. Have a division, a constant set interface, and do the IR integration. In that case, you get something that looks like this. You already see that this is non-local, that as I was advertising, but if you generalize this to not a constant, but an arbitrary case, an arbitrary shape, what it ends up happening is that you can write it generally in this form, where this G is a bulk Green's function that vanishes at the position of the interface. So here you can already see this bilocal form that I was advertising. And well, the fact that this is non-local, that also happens when you integrate UV modes. That also happen in these Randall-Sundrum brane worlds. But in that case, it is known that when the brane is very close to the boundary, then what you get as a world volume theory is something that looks like Einstein, that is local, plus some small, you can do a perturbative expansion and you get perturbatively higher derivatives, as long as you are very close to the boundary. Here, similarly, you can expand these actions very near the infrared. When you integrate infinitesimal, you get something local plus some higher derivatives.
Sorry, can I ask?
Yeah.
Could you explain where the information of the state is encoded in this? I guess if you turn on some sources, G will depend on the sources, probably.
Well, so crucially, I'm doing this integration by keeping the sources in the complement off. So
okay.
Or you can keep them by fixed, but once you do the integration, you are not allowed to change them, right? So because you are not allowed to change the global state once you do the integration.
Okay, and they do affect IR via G,
yes.
or
yes, they do. So here I was assuming that the sources in the complement were off, were 0. And that's what you get, but more generally, you can keep them on, and you can get the functional. I was planning to talk about this later, but I can come back to it.
So I mean, usually when you start computing real-time correlation functions and you're solving your sort of scalar equations, you don't just get, the K-Bessel functions, you get sort of other normalizable pieces which tell you about the state. So in that sense, I'm quite surprised to see that in the third line, you only have the K-Bessel function, because I would have thought you would have had additional contributions which involve the other types of Bessel function solutions, which are telling you about, whether it's retarded, advanced, whatever correlator it is. I guess it's sort of basically the same question as Kyriakos is really. I would expect that to be there.
Yeah, so this term is not a bulk term, but it's localized, no? It's localized, and this comes from imposing, let's say, normalizable boundary conditions in the deep infrared. Like if you imagine pure Poincaré DS, you want having.
Sorry, you still have information on top of that about the state, right? So it's not just the K. Yeah, so you've made a choice there, and I agree that there would be one choice for which this
Yeah,
would
yeah.
be the case, but this is a special state. I think.
Yeah, this is a special state. I agree. So you can start with some other boundary condition in the pure infrared. But what I wanted to point out here is that this term carries out that information that you already have from the global. So in the global perspective, the state that you have, it defines your boundary conditions everywhere, infrared and UV. And you can change it as you want. And when we forget about this infrared, this is the term that carries out that information of what the boundary condition that I would normally put in the infrared. But I agree. I mean, you can change the boundary conditions there, and then this term will change. Okay. Yeah. So another concrete example that we explored was so when you take operators of large conformal dimension, then you can use the geodesic approximation. And so this is very similar to the Wilson loops that I was telling you about at the beginning, in the sense that there are several examples of geodesics that also can exit an entanglement wedge. So there are, I drawing here 3 examples here. This is an example of where the region of interest is disconnected. And I'm in a regime where the regions are far apart, such that the entanglement wedge is the sum of these 2 smaller wedges. And in that case, naturally, if you want to compute a 2-point function where one operator is inserted in one of the regions and the other is in the other, then you will naturally exit the entanglement wedge. This is another example where the region of interest is an annulus. And this is very similar to the Wilson loop that I was showing at the beginning. This is an infinite strip, and then you pick a correlator where the 2 points are along one of the infinite directions. If you pick them very separated, at some point, they will exit the wedge. And I'm not showing here the details, but here you can, as you go and do the exercise, you can clearly see how the IR encodes the length of these portions of the geodesics that exit. And similarly, you can also easily check this connection that I was discussing about the connection or the translation between the 2 different boundary conditions. Okay, so a couple of natural generalizations that we explored. So one was actually connected to what Kyriakos was saying. So here, just important to emphasize that there is a distinction between this tracing over procedure that we normally do versus the integration, the path integral integration that we are doing. So here, the focus, you start on a state. So you define a state on a time slice. You trace over some of the degrees of freedom, and then yeah, the causality tells you what information do you have in the full space-time. Well, here we're doing an integration. We're doing an integration directly in a space-time region. So in order to actually make contact between the 2 approaches, we have done 2 things. First, we have picked the space-time region to be the one that we wanted. And second, we have kept the sources off in the complementary region. That's essentially saying that once we do the integration, we don't have the possibility of changing the state, the global state. Right, so we can relax from the integrating out perspective, we can relax both. So if we relax this, for example, if we allow to keep sources in the complementary region, if we allow to keep them on, then we arrive to a boundary term that is now a functional of these sources. We can do that, but in that case, there is no information loss in this integration. It's just we are just carrying out part of an integral, and that's it. The second generalization is that we can pick up a different space-time region. So in the bulk, you can integrate up not only to the edge of an entanglement wedge, but you can pick any other surface that you want. This is an example that we explored, the constant wall. You can have it curved as you wish. And this is another example that we mentioned. This is actually also makes contact with this tracing over perspective. Here, you imagine starting from a state on this time slice, and you pick some degrees of freedom that are below this cutoff, right? So in the Wilsonian sense, that would be analogous to picking modes, UV modes in momentum space, more or less. And then causality, you can let causality tells you what is the domain of dependence of that portion of the slice that you picked. And then you arrive to this wedge here that I guess it has been explored in other works, but here we call it a momentum wedge. Yeah, and finally, let me mention a couple of ideas that we are still interested. First is the case of Wilson loops, more specifically to make a connection with this work of Ning Bao and company that I was mentioning. Second is to explore more in detail this last example that I pointed out, where now instead of having a wedge associated to a spatial region, you have a wedge associated to a momentum region. I mean, it's not clear that you can define it, so it's an open question if this makes sense or not. And more importantly, so these 2 points. One is going beyond the scalar field example, specifically to include the dynamical gravity. But there are some issues there that we have to overcome and we have to think about. First is implementing invariance under diffuse. Then there is the issue of edge modes, and more drastically, there is the issue that in quantum gravity, it's not clear if you can factorize the Hilbert space. Maybe there is an option, or there is a hope that if we try to include the metric in this description, that we are not able to integrate up to an arbitrary surface, but that these issues will force us to integrate up to just a subset, such that for example, this factorization is satisfied. And finally, going the other way around, we would like to understand more sophisticated examples of this ADS BCFT. Like the example that is out there is a very simple example where the brain is just a constant tension brain. And that's it, but we would like to see what happens when you include higher order derivatives, for example, and if in some of that expansions we can match to the prescription that comes from the bulk using our integration. Yeah, with that, let me stop and
questions?
Thanks for this nice talk. One thing that was not clear for me. Did you analyze this example where the entanglement wedge is bigger than the causal wedge? Like, how do you do that there?
so it's generally bigger, yeah. And
yeah, but so how does your integrate? You're still like, there's no problem with your integrating out to that case where there's
no. I mean, you define the surface that you want to integrate to, and that's it.
So that's the
It's
same
no
as the other examples. There's no subtleties there.
Other questions? Sorry, so maybe a related question. What you presented from the bulk point of view could be done for the causal wedge as well, right?
Yeah.
So do you have anything to say if we have a black hole in a single CFT, a one-sided black hole? Have you thought about applying this idea to the causal wedge of the entire CFT?
So that's one of the ideas that we have is start from, say, a thermofield double and integrate one side and arrive to, I imagine you get something similar to.
Well, in the case, it's a bit more clear what you mean by you trace out the other CFT, right?
Yes.
But if you have a one-sided black hole, it's clear what you're tracing out.
Well, I guess you need to have under control what are the degrees of freedom inside of the horizon and what is the state, the global state. So if you have only one-sided, I don't know. But I mean, for the two-sided, it's more clear.
Mm-hmm. Okay, if there are no more questions, let's thank Juan again.